Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at an alternate form of Taylor's theorem, and we'll use the Taylor's theorem that we proved last time. So last time we introduced this definition of a ck function, which was a function that is k times differentiable, and its kth derivative is continuous. So this was the notation for the kth derivative. And we proved a certain form of Taylor's theorem, which says that if we have a ck plus 1 function for some non-negative integer k, then f can be decomposed as a polynomial part and a remainder part, where the polynomial part is given by this expression and the remainder part is given by this expression. So this is what we did the last time. And now to get to the Lagrange form of Taylor's theorem, we need first a lemma, which will make no sense. But this lemma is designed to get to the Lagrange form, which we haven't even stated, so naturally this does not make any sense. However, this is a very simple lemma, so let's just dive in. So what we have is a continuous function defined on a closed interval a b, and n is some non-negative integer. And then the claim is that there is some t naught strictly between 0 and 1 with this property, this integral, and this integral is the kind of integral that is appearing in the previous page, this thing. So there is some hint as to where this is going. So this integral is equal to that value. Okay, so let's prove it. The proof will elucidate as to what's going on. So define this is 0 to 1 as gx is this integral where we just kind of shift it. So x is a number, so this is just a number for this integral. This function takes t and spits out this value. So we are integrating that function. X is sort of like a number as far as this integral is concerned. So I hope you don't get confused by that. So we have this some definition, this function g. Note that g is continuous. All right, so we have that. And now since phi is continuous, there exist, since phi is continuous and its domain is compact, and this closed interval is compact, we know that there exist points x0 and x1 in the domain of phi such that x0 is the global minima. No, I shouldn't say the global, okay, sorry, such that g achieves its global minima at x0 and it achieved its global maxima at x1. So any continuous function defined on a compact set has this property that it achieves its global minima and maxima. It may be achieved at many points, but it is achieved at least one point. So we have chosen such points x0 and x1. Okay, so once that is the case, note that g of x0 is greater than equal to 0 and g of x1 is less than equal to 0. Why is that? Because if you substitute x0 here, this thing is always non-negative by virtue of the fact that x0 is a global minima. Let me not write an x here. What was written was correct, but let me write it this way. This is better for exposition. So if you substitute x0 here, what have I written? This is not a g, this is a phi. My bad. Sorry about that. So since phi is a continuous function on this compact interval, it achieves its global minimum and maximum. That is a bad typo. So yeah, so now what was I saying? I'm saying that gx0 is greater than or equal to 0. Why is that? Because if you substitute x0 here, then this thing is non-negative through and through, throughout the domain of phi, because of this condition. And if you substitute x1 in place of x0, then because of that, this is always non-positive, and hence overall the integral will also be non-positive. So we have these inequalities. So now there are three cases. Case 1 is that gx0 is 0. So what happens in this case? This integral is 0. But then I claim that this implies that the integrand, meaning the thing inside, this is 0 for all t in the closed interval 0, 1. Why is that? Now this is a continuous function, and it is non-negative throughout this domain 0, 1. So if its integral is 0, then the function itself must vanish everywhere, because if you have a continuous function which does not vanish at a point, which is, let's say, positive at some point, then it remains positive in a neighborhood, and since it is non-negative everywhere else, the integral will be at least that area which you see. I mean, I'm just arguing somewhat lightly, but I hope you get it. So if you have a continuous function which is non-negative and its integral is 0, then the function better be 0 throughout the domain of integration. So what does this mean? This means that phi is actually a constant function, because this implies that phi is equal to phi x0 everywhere. Phi t equals phi x0 for all t in 0, 1. So in this case, such a thing happens, and therefore, if you just use this equation, you'll see that this happens. This trivially happens in that case, because phi t naught just becomes a constant. Phi t is equal to phi t naught for each t, so this just becomes a constant, comes out, and if you integrate the thing inside, you get the expression on the right hand side. So this is case 1. Similarly, case 2 is that gx1 is 0, and it's very, very similar, so I leave the details. Case 3 is that the previous two cases don't occur. So gx0 is non-zero and gx1 is non-zero. So thus, as we saw earlier, this forces that this is actually negative. No, sorry, not negative. This is actually positive, and the second one is negative. So the function g takes a negative value and a positive value, but g was a continuous function. So by intermediate value theorem, thus by the intermediate value theorem, we have some t naught strictly between 0 and 1, such that gt naught is 0. Therefore, the integral 0 to 1, and this is gt naught, which is integral 0 to 1 n, and here we have a phi t minus phi t naught equals 0, and it's just doing the algebra implies. So this implies that this integral is actually that integral. which gives us this. So yeah, so it basically is just intermediate value theorem. We just have to analyze the boundary cases separately. So these are the pesky boundary cases. This is the main idea using intermediate value theorem. Anyway, so we have that. And now we can finish the proof of this Lagrange form. The first we have to state the Lagrange form. So what is it? So here is the theorem, the Lagrange form of Taylor. So let f be a ck plus 1 function where k is some non-negative integer. Then yeah, so I is an open interval. So then for any a and x in I, we have f of x equals the polynomial part plus the remainder part, where the remainder part will look a little different, look a little bit more civilized than it did in the previous formulation. So this is x minus a to the power k plus 1, and here we have a c for some c strictly between a and x. So for some c strictly between a and x. So I don't use this a comma x notation because that implicitly implies that a is less than x. So I'm not using that notation because I don't know if a is less than x. A and x could be not necessarily in that order. So this is the Lagrange form of Taylor, and the proof is very simple now. The proof is, so this is already our pk, the first part. So we just need to show that rk looks like this for a suitable c. So what is rk? Rk of x is, let me see what is the expression. So rk of x is actually x minus a to the power k plus 1 divided by k factorial integral 0 to 1 minus t to the power k f k plus 1 a plus t x minus a dt. So that's what it is, and now think of this as phi. Think of this as phi in our previous lemma, this lemma. So by that lemma we know that this is equal to x minus a k plus 1 upon k factorial 1 upon k plus 1 phi of a plus t naught x minus a for some t naught strictly between 0 and 1. So this thing now we can call c. C is now strictly between a and x. C depends on x, so maybe I should also qualify that with a subscript. And this is simply this guy, x plus 1 upon the numerator upon a k plus 1 factorial. This is c. So this c depends on x, of course. All right. So this is what we get. And that's it. I mean, there's nothing more to say here. The point of this theorem is, or rather when you apply it, what happens is, suppose you have some kind of control over these derivatives. Then you know the behavior of f fairly precisely. Suppose the derivatives are small, let's say uniformly bounded or something. Then this is a good approximation of the function. That is basically the point. So let me just see if there is anything else. There is nothing else. This is the Lagrange form. That's it. As usual, like, comment, share, subscribe. I also have Patreon. The link. See you next time.